Today, we'll be looking at a paper called Style Normalization and Restitution for Generalizable Person Re-identification. So this paper tackles the problem of person re-identification, or ReID. And ReID is a task that aims at matching and identifying a specific person across cameras, times, and locations. So what it basically means by this is, let's say that you have two images of a same person, and they are taken from a different camera angle, different pose, different hue, different illumination, different contrast of the image. And despite these differences in the images, the ReID aims at correctly classifying that these two are from the same person. And if they're from the different person, it needs to correctly identify that these two are from a different source person. So through the advancements in CNN or deep learning in general, this ReID task works pretty well on the training dataset, but it suffers from significant performance degradation when testing on a previously unseen dataset. So what it means by that is, let's say that you trained a ReID model on camera settings with high illumination and low hue and bad camera quality and all these in general. So you have a specific camera setting where the images were taken from, and you train an image on it. Then of course, on the validation set where the camera settings the same, or the test set, since the camera settings are all the same, the models trained on the training set would perform pretty well on the validation set as well. But when applying this model in a different real-world camera where the illumination, hue, contrast, saturation, camera quality, all these have a different setting, then it is obvious that because of this domain gap, the model trained here won't perform as well in this part of the domain. So these style discrepancies across domain and datasets usually hinder the achievement of high generalization capabilities. So for ReID, it is important to minimize or mitigate this domain gap in the real-world dataset, such as differences in illumination, hue, contrast, saturation, or quality. So that is exactly what this paper is trying to achieve. To achieve this, the paper suggests a module called Style Normalization and Restitution, or SNR. And what SNR is, basically, you have this input feature and you want to remove the style information from it. So let's say that among this input feature, these red features represent identity relevant features, and these green ones are identity irrelevant features. So first step of this SNR module is the style normalization, which removes the style information from the features. So you can see that all these informations which were related to the style have been removed from the input feature. But not all styles are bad at training the ReID model. There might be some certain styles that are necessary or important in well classifying between different identities of the people. So to reintroduce these deleted features selectively, they perform ReID guided style restitution, where the deleted features are reintroduced like this. So finally, we have so at the output of the module is it's the same dimension with the input, but all the identity irrelevant features are disappeared, and only the ones with identity relevant features are remaining. Now let's look into detail about how this works. Yeah, so this SNR module is, since it has the same output dimension with the input dimension, it can be plugged in any part of the convolution CNN. So the paper put 4 SNR modules, SNR 1, 2, 3, 4, in the intermediate features of the convolutional neural network. And the other parts are basically the same with any other traditional ReID models. So let's look at this SNR part in detail. So the first part, style normalization, is done by a phase called instance normalization. So what is instance normalization? So instance normalization is just yet another normalization technique in training a deep neural network, just like batch norm. So batch norm, when you have a batch size by channels by height by width dimension of a intermediate feature, then you normalize the feature by subtracting the mean and dividing it by the standard deviation across the batch and the height and width dimension. So by doing this across the batch and height and width dimension, you have a zero mean and standard deviation of a value 1. And then you linearly transform this normalized feature by multiplying gamma and adding beta, which are both learned parameters. So by doing this, batch norms are shown to really accelerate the convergence of the training, and it is basically used in a lot of modern deep learning architectures. And even though there are many reasons why batch norm accelerates training, but one reason is that since it normalizes and does a linear transformation across the batch axes, it can use the information from other images in the same batch. So this inter-batch representation allows the batch norm to perform pretty well. Although there are many other reasons, that's one of the reasons why. And a different type of normalization is instance normalization, where it's basically the same formulation with batch norm, but instead of normalizing across these axes, it normalizes across only the height and width dimension, and of course multiply by gamma and add beta to do the linear transformation. So since instance norm doesn't incorporate any batch information, it tends to perform worse than how batch norm does. But that is not the case, but batch norm isn't the thing we want in the SNR module. Since styles of the images are image specific, we don't styles in the images are just image specific. So let's say that you have a batch of images and the style of the images are unique for each of these individual images. So they should not be correlated, or the information should not be should not be influencing the images in the other batch. So in other words, in order to only isolate the style information, we should not incorporate any batch information, just like what batch norm does. So that's the reason why instance norm is pretty useful in dealing with styles, because it only works across the dimension of a single image. It does not work across multiple batches which contain different styles, and normalizing the features across the batch axes that has multiple styles. Of course, that will not work when we try to identify the individual styles of the individual images in the batch. So that's the reason why instance norm is used frequently in a lot of style transfer literatures. And one main example is adaptive instance norm, or ADA in short, which tackles the problem of fast style transfer in arbitrary styles. So what that task basically is you have these two images, content and style, and you want the style of the style image to be applied to this content image while preserving the style. So what ADA-in does is it allows a single model to do this task in an arbitrary style, and their ADA-in module basically normalizes the feature via instance norm. And you have this multiplying by gamma and beta part. But instead of learning this gamma and beta and having it as a fixed value, we condition gamma and beta on the style image. So you have this style image feature, and you go through several CNN transformations, and then produce this gamma and beta vectors, which are multiplied and added here. So this can be considered as the instance norm or the normalization part, removing the style information from the content image. Oh, and by the way, this is the content image feature. So this removes the style information from the content image and reintroduce the style from the style image. So from this process, we can see that instance norm is thought of something as a style normalization in a lot of style transfer literatures. So basically, the style normalization phase is just instance normalization. And now what's important is the style restitution phase. So let's see it again. So this input feature f goes through instance normalization to produce a feature of f squiggly, or f tilde, but I'll just call it f squiggly. And then, and as mentioned before, this instance norm, even though it removes the style information and reduces the domain gap, some of the style information might actually be related to the identity of the person in that image. So that's the part where style restitution phase comes in. So basically, the features removed from f squiggly is so basically the feature removed from f to become f squiggly is f minus f squiggly, denoted as the residual feature r. So what we want to do is, among these r, which are the style information, we want to selectively choose the features from r that are actually relevant to the identity of the person, and reintroduce them back to f squiggly by simply adding them, simply multiplying them. And how this r is and the way this paper does to selectively choose parts of this R is by multiplying it with a vector A across the channel axes. So A is a vector in the range of 0 to 1. And by this, it selectively chooses the feature from R that are related to the identity, and ignores, by producing value of 0, on features that are irrelevant to the identity. So the way we produce this A is simply performing a global average pooling on this R feature, which has a dimension of h by w by c, to get a feature of size c, and then going through several MLP layers to produce A, which also has a size of c. So basically, this A is conditioned on the residual feature R, so that the network can learn what features among R are important. And then by multiplying this A to the feature R, we get R plus, which are the identity relevant residual features. And of course, when multiplying by 1 minus A, you get R minus, or identity irrelevant residual features. Yeah, so this can be considered something similar to SE, or squeeze and excitation network. So this is basically a channel attention. So after you obtain this A and obtain this R plus, you just simply obtain this R plus, you get a enhanced feature by reintroducing R plus to F squiggly by just adding them. So you have this F squiggly plus, which is the enhanced feature. However, this itself might not cause the network to learn a mapping from R to A that can learn to distill the information, distill the identity relevant feature R plus. Therefore, this paper suggests another regularization called dual causality loss constraint. So let's look in this in detail. So after restituting the identity relevant feature R plus to the normalized feature F squiggly, we obtain f squiggly plus, which we expect it to be more identity relevant and more discriminative in terms of ReID, of course. But on the other hand, when we introduce r minus to the f squiggly and obtain f squiggly minus, we expect this to be less discriminative in terms of ReID. So this expectation can be explicitly regularized in the network training through a dual causality loss. So what this basically does is shown in this diagram, where these are the features. These are the features from different images, and the same colored ones are of the same identities. And what we expect is that by adding this r plus, since we're removing the style information, we expect the features from the same identity to be closer to each other. And when we add r minus, we expect the features from the same identity to be further away from each other, like this. So this part of the regularization and this part of the regularization are each achieved by the plus SNR loss and minus SNR loss. So let's look into this loss in detail. Since we want the features obtained from f squiggly plus among the same identity to be closer and the ones in the different identity to be further away, what this paper does is, within the same mini batch, they sampled 3 images. First, an anchor sample A and a positive sample P. And these 2 images are from the same identity. And then a negative sample N, which has a different identity from the anchor sample. So we want to, for the first regularization here, we want to make it so that the features of each of these from f squiggly plus, these are closer to each other, and these are further from each other, while in f squiggly minus, we want to do the opposite. So in the plus SNR loss, we want to achieve these 2 loss functions, and we can ignore, and for the soft plus part, just to make the training easier, the soft plus part is put to make these 2 values not negative, so we can just ignore this for now. So to minimize this plus SNR loss, it basically means that we want this term to be bigger than the term left here, and we want this term here to be bigger than the term here, so that we can minimize this SNR plus loss. So what does it mean by this? So basically, the plus features or the enhanced features should have a smaller distance between the same identity than it is from the features without the enhancement or without the restitution. So basically this part means that we want the same ones to be closer than how it is in here. And then the second part is we want the distance from the enhanced feature among the different identities to be bigger than how it is in the distance in the non-restituted features. So this basically means that we want these 2 distances to be further away than how it is in the original feature distance. So that's the way the paper achieves the first regularization through the plus SNR loss, and the second part of the feature f squiggly minus, where the contaminated feature is reintroduced, is basically done by doing the opposite. We want to maximize this and maximize this, where the distance between the same identities should be larger in the contaminated feature f squiggly minus, and the distance between the anchor sample and the negative sample, or the distance between features in the different identity should be smaller in the corrupted feature, contaminated feature. So each of these loss terms plus SNR and minus SNR are called the clarification loss and the destruction loss. So by having these two loss terms together with a traditional ReID loss, this is basically the framework this paper suggests for this SNR module. So you can see like this. This is the traditionally used ReID loss function, and then the SNR loss function, basically SNR negative plus SNR plus, and we add them across the 4 SNR blocks in the module, because remember there are 4 SNR modules. Therefore, there can be 4 F squiggly plus and F squiggly minuses produced for each of the SNR blocks. So this is basically it. That's how this SNR framework works. And they found performance gains in a lot of datasets like this. And you can see that compared to the instance norm, compared to only using the instance norm, the SNR module performs way better than that. And there were some very interesting experiments they did. For example, the figure 4 here is the visualization of distributions of the intermediate features. So let's say, this is the feature F, which is prior to the SNR module, and this is the F squiggly, which is after the instance norm or the style normalization phase, and this is the F squiggly plus, where it does the restitution. And you can see that in the input feature F, so this is the intermediate feature where the red is from a source domain and the green is from the target domain. And you can see that because of the domain discrepancies, the feature distribution are far apart, like this here and this here. And ideally, we want the style information to be removed, so we want these two features to be in the same part. So that's exactly what happens when these features go through instance normalization, where both the source domain and the target domain lies in the same space. So you can see that the domain-specific informations are removed. But now when you see in this purple part and the yellow part, which represents the features for images of the same ID, they are more further apart. So you can see that even though F squiggly removes the style information, it removes too much information that the discriminative performance degrades. Now that's the reason why we want to introduce this restitution part, where compared to F, the domain discrepancies are still reduced. But the features of the same IDs are closer to each other, like this. So you can see that, so this experiment was pretty interesting because it clearly shows the effect of individual modules in the SNR module, like the instance normalization and the restitution part. And then next is the activation map of the different features within the SNR module. So this seems like a class activation map, or CAM, which visualizes which part of the image actually contributed for the network to make a certain decision. And you can see that this is the original feature F squiggly, and it made its decision through looking at this part of the image. And you can see that it also made the decision by looking at quite irrelevant features of the image, like the ground here. So by performing the restitution part by adding the R+, you can see that the features are more focused on the body part of this image. And when we add R-, it does the complete opposite, where it focuses only on the irrelevant parts of the image, like this. And the same goes through this image as well. And the second image really shows the power of SNR. So you can see that this is the class activation map in the original image. And without the SNR module, when the contrast of the image changes, or when the illumination of the image changes, the class activation maps are quite different from how it is in the original. So this shows that the style information are actually playing a role in the baseline, which contaminates or worsens the discriminative performance of the model in different domains. But when we introduce SNR, as expected, the differences in the class activation maps are smaller. They look pretty similar, like this. So this was a pretty interesting visualization. And these are some ablation studies that show the effect on, first, the effect of the dual causality loss. So this is the baseline. This is the baseline performance, and this is the performance where it's just SNR without the SNR loss. And it was quite interesting because despite not having the dual causality loss, it still performs pretty well compared to the baseline. So I think this SNR module can not only be applied in the ReID module, a ReID task, but it can be just applied in just general image-related tasks where we want to remove the style-related information for better performance in different domains, like autonomous car driving. So this was the performance when there was no SNR loss, and this was the performance when there was no plus SNR loss and minus SNR loss. So, and that still performs better than not having the SNR loss at all. And when combining these loss terms together, we get the best performance of this. Now the next ablation study is on where to add the SNR. So this is the baseline, and you can see that just adding the SNR module in all 4 stages yield in the best performance. And next, they performed ablation studies on different disentanglement designs in the SNR module, where the baseline, they extract R plus through putting the R feature in a module called G, and then obtaining R plus. And then R minus is complementary to R plus, which is simply subtracting it from 1 to obtain R minus. And the different designs in this module, such as SNR conv, disentangles the residual features R into R plus and R minus through 1-by-1 convolution followed by ReLU like this. And the SNR G squared uses 2 unshared gates, G plus and G minus, to obtain R plus and R minus respectively. So it means that these two aren't related to each other, and when you add R plus and R minus up, they don't add up to 1. And since these two won't be shared with each other, it is quite expected that this won't perform as well as the original SNR design. And as expected, you can see that the original SNR design performs better than all these other design choices, including the baseline. So overall, the paper says that SNR works pretty well, and it can be applied in complementary with pre-existing domain adaptation techniques in person re-identification, like MAR, which achieves the best performance out of all methods. So overall, this SNR paper was pretty interesting in the way it introduces style normalization and restitution in order to remove the identity irrelevant features from the feature space. And even though this paper introduced this SNR in the task of person re-ID, I think if we don't use the dual causality loss, this SNR approach can still be applied in a lot of computer vision tasks where style information aren't really that important. So overall, this was a pretty interesting paper. And if you liked the video, please leave a like. And if you have any comments or suggestions, please leave them in the comment section below. Thank you.